Hello, in this lecture we will answer two questions. In the first question, we'll find out the area of this rectangle EHQF, and in the second question, we will find out the area of this circle using two different methods. So we'll start with the first question. In the drawing, we have this big rectangle EFQH. Inside this big rectangle, we have three circles. The radius of this small circle is equal to 5 units in its length. The radius of this medium circle is equal to 6 units in its length, and the radius of this big circle equals to 8 units in its length. Again, our test is to find out the area of this big rectangle EFQH. So first of all the angles inside any rectangle are right angles. So those four angles are all right angles. So this is a right angle. This is also a right angle. This is a right angle. This is also a right angle. We will implement all one in our drawing. According to rule 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle. OM is the radius of this circle, that is equals to R. The radius OM that is equals to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. So we use rule 1 a lot of times in our drawing, so I'll explain only one time how we implement rule 1 in one case, and then we implement it in our drawing without any explanation. So for example, this is the medium circle. The radius of this medium circle is 6. The radius QB is equals to 6. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this medium circle. And whenever your radius is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BQ. If HQ is perpendicular to BQ, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule 1. Likewise, according to the same rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. This angle also equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we will define the point of tendency of tangent FQ with this big circle. This point is point T, and we join points S and T together by a straight line. ST is of course the radius of this big circle, that is equals to 8. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So when doing this construction, we're going to do quadrangle CFTS. Inside quadrangle CFTS, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4-piece rectangle. In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4-piece rectangle must be equal to 90 degrees in its size. So inside quadrilateral CFTS we have 4 rectangles. Therefore we relate to quadrilateral CFTS as rectangle. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle CFTS, side ST must be equal to the opposite side CF. But ST is 8, therefore the opposite side CF must be also equal to 8 units in its length. In the next step, we define the point of tendency of tended edge Q with this big circle. This point is point H, and we join points S and H together by a straight line. SH is of course the radius of this big circle, that is equal to 8, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the lower quadrangle STQH, we have 1, 2, 3 rectangles, and therefore this 4-piece rectangle must be equal to 90 degrees in its side. So therefore quadrangle STHQ is a rectangle, because it has 4 rectangles. So actually, we found out that the big angle CSH, this is the big angle CHS, equals to 90 degrees plus 90 degrees, that is 180 degrees. And know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, CH is a straight line. Again, CH is a straight line. So as you know, CH is a straight line. So actually, the big shape EC we define this point as H, but we have only F point H here, so I'll change the letter H to L. So this point is point L. So this shape ECLH has 4 sides, 1, 2, 3, 4, and therefore shape ECLH is a quadrilateral because it has 4 sides. The quadrilateral ECLH we have 1, 2, 3, 4 rectangles, and therefore quadrilateral ECLH is a rectangle. So as you know, the big quadrilateral ECLH is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ECLH, side CL must be equal to the opposite side EH. But CL in total equals to 8 plus 8, that is 16, therefore the opposite side EH must be also equal to 16 units in its length. E edge is the width of this big rectangle EFQL. So if we found out that the width of this rectangle EFQL equals to 16 units, the only thing that is left to find is to find out the length of this big rectangle, that is EF. After we find the length, the width times the length is the area of this big rectangle EFQH. That is the area that we are looking for in this question. In the next step, we will extend the radius BQ of this medium circle by a straight line until it touches side EF of the big rectangle. By doing this construction, we're going to do, we'll define the touching point of the extended radius BQ with this circle. This point is point S. So by doing this construction, we're going to do quadrangle ESB edge. Inside this quadrangle ESB edge, we have 1, 2, 3 rectangles, and therefore this fourth angle must be also equal to 90 degrees in its size. Likewise, in this quadrangle SC and edge, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size. So in this quadrangle ESB edge, we have 4 rectangles, and therefore we relate to this quadrangle as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ESB edge, side E edge must be equal to the opposite side SB. But E edge is 16, therefore the opposite side SB must be also equal to 16 units in its length. So you know, if we found out that side SB equals to 16 units in its length. In the next step, we will do another construction. That is to say, from point P, that is the center of this small circle, we will go perpendicular on SB. Again, from point B, we will go perpendicular on SB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and SB. This point is point X. By doing this construction, we rendered the small quadrangle ASXP. Inside this small quadrangle ASXP, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. Therefore, quadrangle ASXP is a rectangle, so it is known. The small quadrangle ASPX is a rectangle because it has 4 right angles. But we know that the opposite sides of a rectangle are equal to each other. So in the small rectangle APXS, side AB must be equal to the opposite side SX. But AP is 5, therefore the opposite side SX must be also equal to 5 units in its length. What is the length of this missing nice element XQ? From the drawing it is very easy to see that XQ equals to SB minus SX minus QB. Again, XS equals to SB minus SX minus QB. So later on we should find out that the length of the 97XQ is equal to SB minus SX minus QB. So in total XQ equals to SB is 16 minus SX is 5. 16 minus 5 is 11 minus QB, that is 6, and 11 minus 6 is 5. So if you found out that XQ equals to 5 units in its length. In the next step, we will join point P and Q together by a straight line. Point P is the center of this small circle. Point Q is the center of this medium circle. Therefore, PQ is the distance between the centers of the small circle and the medium circle. Those two circles touch each other externally in this point. We define the touching point, this point Y. And whenever you have an external latch between two circles like here, you can implement Rule 10. So repeat quickly on Rule 10. According to Rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing, we have two circles. They touch each other externally at point K. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects the centers together is of course the straight line OM. And according to this Rule 10, the straight line OM must pass through point K, that is their touching point. Again, the straight line OM must pass through their touching point, this is point K. Or OKM is one straight line. Again, OKM is one straight line according to this Rule 10. So we can implement Rule 10 in our drawing. Why put in our drawing? The center of this circle, small circle is at point P, the center of this medium circle is at point Q, and the straight line that connects the centers together is of course the straight line PQ. This straight line PQ must pass through the attaching point, that is point Y. Or PYQ is one straight line. PYQ is one straight line. So if PYQ is one straight line, it means that PQ equals to PY plus YQ. Again, PQ must be equal to PY plus YQ. PY is the radius of this small circle, this is equal to 5. QY is the radius of this medium circle, this is equal to 6. Therefore, PQ in total equals to PY, that is 5, plus YQ, that is 6. 5 plus 6 is 11. So PQ in total equals to 11 units in its length. PQ equals to 11 units. In the next step, I'll copy the right green triangle PXQ in a new page, and we'll implement on this right green triangle the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT, evaluation for Pandora Store. So actually, this is the right main triangle PXQ that according to the original drawing. This right triangle PXQ PQ squared, that is the square of the hypotenuse, equals to PX squared plus XQ squared. So I write it down. PQ squared, that is the square of the hypotenuse, equals to PX squared plus XQ squared. PQ equals to 11, now for PQ squared is 11 squared, that is 129, that is 121 of course, 11 squared is 121, and it is equals to PX squared. PX is the missing side, so we leave it as it is, so it is PX squared plus XQ squared. XQ is 5, therefore XQ squared is 5 squared, that is 25. So in total we should find out that 121 equals to PX squared plus 25. Here we subtract 25 from this equation, and we get that 121 plus 25 is 96, so 96 equals to PX squared. Here we will substitute 96 by 16 times 6, and we get that 16 times 6 equals to PX squared. So here we take out of this equation, and we get that the missing side PX is equal to the square root of 16 is 4, so inside the root we left only with 6. So if you found out that the missing side PX equals to 4 times square root of 6 units in inside. This is 97px, that is equals to 4 times square root of 6 units in its length. So, quadrilateral APXS is a rectangle, and know that the opposite sides of a rectangle are equal to each other. So in rectangle ASXP, side PX is equal to the opposite side AS. Side PX equals to the opposite side AS. But PX equals to 4 times square root of 6, therefore the opposite side AS must be also equal to 4 times square root of 6 units. We will define the touching point of tangent EH with this small circle, this point D, and we join points P and D together by a straight line. PD is of course the radius of this small circle that is equals to 5, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the small quadrangle AEDP we have 1, 2, 3 degrees, and therefore this fourth angle must be also equal to 90 degrees in its size. And therefore, for the other AEPD is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So rectangle EAPD, side PD must be equal to the opposite side AE. But PD is 5, therefore the opposite side AE must be also equal to 5 units in its length. In the next step, we join points Q and S together by a straight line. Point Q is the center of this medium circle. Point S is the center of this big circle. So QS is the distance between the centers of the medium circle and the big circle. We have an external notch between the medium circle and the big circle, that is to say they touch each other externally at this point. We define this point, that is their touching point, as J. So here we can implement rule 10. Whenever you have an external notch between two circles, you can implement rule 10. According to rule 10, the straight line that connects the centers of those two circles together, that is the straight line SQ, must pass through their touching point, that is point J. Again, the straight line SQ that connects their centers together must pass through point J, that is their touching point, or SJQ is one straight line. SJQ is one straight line. So if SJQ is one straight line, it means that SQ must be equal to SJ plus JQ. JQ is the radius of this medium circle, that is 6. SJ is the radius of this big circle, that is 8. And according to rule 10, SQ equals to SJ, that is 6, plus JQ. Again, according to rule 10, SQ equals to SJ, that is 8, plus JQ, that is 6. 8 plus 6 is 14. So SQ equals to 14 units in its length according to rule 14. According to rule 10, of course. Again, SQ equals to 14 units according to rule 10. In the next step, we will do a construction, that is to say from point Q, that is the center of the medium circle, we will go perpendicular on CL. Again, from point Q, we will go perpendicular on CL. We define the touching point of the perpendicular from point Q and CL. This point is point Z. By doing this construction, we get the lower quadrangle QZLB. This is quadrangle QZLB. Again, from point L and from point Q to perpendicular on CL, and therefore, according to our construction, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrangle QZLB, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees in each side. Therefore, this quadrangle QZLB is a rectangle because it has 4 right angles. So write it down. This is quadrangle QSLB, this is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle QSLB, side QB must be equal to the opposite side ZL. But QB6, therefore the opposite side ZL must be also equal to 6 units in its length. This is side ZL that is equal to 6 units in its length. So what is the length of this short line segment SZ? SZ equals to SL or ZL. Again, SL equals to SZ equals to SL minus ZL. And again, SZ equals to SL minus ZL. So if you don't, know that the length of the short line segment SZ is equal to SL minus ZL. So SZ, the short line segment SZ is equal to SL. SL is the radius of this big circle that is 8 minus ZL. ZL equals to 6. So SZ equals to 8 minus 6, that is 2. So SZ, the short line segment SZ equals to 2 units in its length. In the next step, I'll copy this ring rectangle SZQ in a new page, and we'll implement in this right rectangle QSZ, the Pythagoras theorem. The hypotenuse QS is equal to 14. The short side SZ is 2, and QZ is the missing side. Here by PT is the derivation for Pythagoras theorem. Okay, this is the right main triangle QSZ that is coming from the original drawing, and this right triangle QSZ, ZQ square, SQ square, that is the square of the hypotenuse, equals to SZ square plus ZQ square. So write it down. SQ squared, that is the square of the hypotenuse, equals to SZ squared plus ZQ squared. The hypotenuse SQ equals to 14 units in its length. Therefore, SQ squared is 14 squared, that is 196. And it is equal to SZ squared. SZ is 2. Therefore, SZ squared is 2 squared, that is 4. Plus ZQ squared. ZQ is the missing side, so leave it as it is. That is plus ZQ squared. So in total we should find out that 196 equals to 4 plus ZQ squared. Here we subtract 4 from this equation and we get that 196 plus 4 is 192 equals to ZQ squared. We will substitute 192 by 64 times 3. So 64 times 3 equals to ZQ squared. Here we take out all those equations and finally get that ZQ equals to the square root of 64 is 8. So inside the root we left only with 3. So total we should find out that ZQ equals to 8 times root of 3 units in its length. This is side ZQ that is equals to 8 times root of 3 units. We focus on the lower quadrangle SC ZQ. Inside this lower quadrangle SC ZQ we have 1, 2, 3 right angles. Again, 1, 2, 3 right angles. And therefore this fourth missing angle must be equal to 90 degrees in its size. So quadrangle SZ, SC, ZQ has 4 right angles, and therefore we are left to this quadrangle SC, ZQ as a right angle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle SC, QZ, side QZ must be equal to the opposite side SC. But QZ is 8 times root of 3, therefore the opposite side SC must be also equal to 8 times root of 3 units in its length. So if you found out that the length of rectangle EFQH is equal to EF, but EF equals to 5 plus 4 times root of 6 plus 8 times root of 3 plus 8. So we have the length, we have the width that is 16, and the length times the width is the area of this rectangle EFQH. That is the area that we are looking for in this question. So I write it down. If you found out that the area of this big rectangle EFQH is equal to the width of the rectangle times the length. The width of the big rectangle EFQH is the edge. The width is the edge. And the length is the F. Yeah, the length is the F. So the area of the big rectangle EFQH equals to the width EH times the length EF. But we already found out that EH equals to 16 times the length EF. EF equals to EA plus AS plus SC plus CF. If you found out that the area of rectangle EFQH equals to the width, that is 16, times the length, that is EA plus AS plus SC plus CF. So the area of the big rectangle EFQH equals to the width, that is 16, times EA. EA is 5 plus AS. AS is 4 times root of 6 plus SC. SC is 8 times root of 3 plus CF. CF is 8. So in total, if you all know that the area that we are looking for in this question, that is the area of the big rectangle EFQH, is equal to the width, that is 16, times the length, that is 5 plus 4 times root of 6 plus 8 times root of 3 plus 8. This expression in total equals to 586.47 square units. So we should find out that the area that we are looking for in this question, that is the area of this big rectangle EFQH, is equal to 586.47 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. In the drawing, we have a circle. This is called AB, that is equal to 8 units in its length. This is called PQ, that is equal to 6 units in its length. This is angle PMQ, that is a right angle. Again, our task is to find out the area of this big circle. So first of all, I will present to you Rule 29, and we will implement Rule 29 in our drawing. According to Rule 29, equal angles that subtend on the same arc are equal to each other. In the drawing, we have a circle. This is peripheral angle BDC. This is equal to alpha degrees in its size, and it subtends on this arc BC. Likewise, we have another perpendicular, this is perpendicular BEC, is equals to beta degree inside, and perpendicular BEC also subtend on the same arc, arc BC. And because of the fact that those two perpendiculars subtend on the same arc, that is arc BC, they must be equal to each other in their sizes. That is to say, alpha equals to beta. Okay. So according to this rule 29, peripheral angles that subtend on the same arc are equal to each other in their sizes. Those two peripheral angles subtend on the same arc, RBC, and therefore they are equal to each other in their sizes. That is to say, alpha equals to beta. So we can actually implement rule 29 in our drawing. Well, if we focus on arc BQ, this is the red curve, that is arc BQ. We have peripheral angle BAQ that subtend on arc BQ. Again, peripheral angle BAQ subtend on this red arc, arc BQ. Likewise, we have another peripheral angle BPQ that subtend on the same arc, arc BQ. And because of the fact that those two peripheral angles subtend on the same arc, arc BQ, they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. According to rule 29, because they subtend on the same arc, arc BQ. In the next step, we'll focus on this arc, arc AP. So the black curve is RKP. This is peripheral APQ that subtend on this arc, RKP. Likewise, we have peripheral PBQ that also subtend on the same arc, RKP. And because of the fact that those two peripheral subtend on the same arc, RKP, they must be equal to each other in their sizes according to rule 29. So if we define the size of this peripheral APQ as beta, then the size of this peripheral ABP must be also equal to beta according to rule 29 because they subtend on the same arc, RKP. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle is a right angle, therefore this angle must be also equal to 90 degrees in its size, because they are equal to each other. So in this right angle ABM, the sum of the angles must be equal to 180 degrees. It is true in any triangle, therefore it must be also true in this triangle, triangle ABM. So which angles we have with the right triangle, triangle ABM? We have angle alpha plus angle beta plus 90 degrees. In total, the sum of those three angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle ABM, alpha plus beta plus 90 degrees, in total it must be equal to 180 degrees. Here we subtract 90 degrees from this equation and we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we will multiply this equation by 2 and we get that 2 alpha plus 2 beta equals to 90 degrees times 2 is 180 degrees. So in total we should find out that 2 alpha plus 2 beta equals to 180 degrees. And again, 2 alpha plus 2 beta equals to 180 degrees. In the next step, I'll present to you rule 13, and we'll implement rule 13 in our drawing, but before that, we'll define the center of this circle. This point is point O. According to rule 13, the central angle is twice as large as the peripheral angle subtended on the same chord. On the same chord or same arc, it doesn't matter. Because if it's subtended on the same chord, for example AB, it must be also subtended on the same arc, that is arc AB. So, according to rule 13, in the drawing we have a circle. This is peripheral angle ACB. It is equal to theta degrees in its size. This is central angle AOB. A central angle is an angle that its vertex is at the center of the circle. This is the say point O. And its legs, its two legs, are the radii of the circle. Okay, so central angle AOB subtend on the same arc AB, and according to this rule 13, the size of the central angle AOB that subtend on the same arc AB, exactly like peripheral angle AOB, must be twice as big as peripheral angle. This peripheral angle that subtend on the same arc AB. The size of which peripheral angle ACB is theta, therefore the size of the central angle must be equal to 2 theta. So according to rule 13, the size of a central angle is twice as big as the size of the peripheral angle that subtend on the same arc. Okay. We can implement rule 13 in our drawing. First of all, I'll create central angle AOP. Repeat again, a central angle is an angle in the circle that its vertex is in the center of the circle and its two legs are the radii of the circle. So this is central angle AOP. Central angle AOP subtend on arc AP. Again, central angle AOP subtend on arc AP. But we also have peripheral angle AQP. This is peripheral angle AQP that subtend on the same arc AP. And according to rule 13, the size of the central angle AOP that subtend on the same arc AP, exactly like peripheral angle AQP, must be twice as big as the size of peripheral angle AQP that subtend on arc AP. So the size of peripheral angle AQP is better. Therefore, the size of the central angle AQP that subtend on the same arc AP must be equal to 2 beta. According to rule 13, of course. We create another central angle. The central angle MOQ. This is center angle BOQ that subtend on arc PQ. But we also have center angle, also have peripheral angle BAQ that subtend on the same arc BQ. And according to rule 13, the size of center angle BOQ must be twice as big as the size of peripheral angle BAQ that subtend on the same arc BQ. The size of peripheral angle BAQ is alpha. The size of center angle BOQ must be equal to 2 alpha. According to rule 13, of course. In the next step, we define the center angle QOP. This angle is X, and we define the center angle POA. This angle is Y. We have the rule that says that the sum of the angles around any point is equal to 360 degrees. I repeat again. The sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point O, that is the center of this angle, must be equal to 360 degrees. So which angles we have around point O? We have this angle that is 2 alpha plus this angle that is 2 beta plus this angle that is X plus this angle that is Y. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that I mentioned. 2 alpha plus 2 beta plus X plus Y. In total, they must be equal to 360 degrees. But we have already found out that 2 alpha plus 2 beta equals to 180 degrees. Therefore, we can substitute 2 alpha plus 2 beta here by 180 degrees. So 180 degrees plus X plus Y, in total, they are equal to 360 degrees. Here we subtract 180 degrees from this equation. And we get that X plus Y equals to 360 degrees minus 180 degrees is 180 degrees. So we found out that X plus Y equals to 180 degrees. In the next step, I will present to you rule 30, and we will implement rule 30 in our drawing. According to rule 30, center angles that subtend on equal arcs are equal to each other. In the drawing, we have a circle. This is center angle COD, that is equal to alpha degrees in its size, and it's subtend on chord CD. Again, center angle COD, subtend on chord CD. Likewise, we have another center angle, that is center angle EOB. This is center angle EOB, that is equal to beta degrees in its size, and it's subtend on chord AB. According to this rule 30, if AB equals to CD, that is to say those two center angles subtend on equal arcs, then alpha equals to beta. Then they are equal to each other and their sizes. So according to rule 30, if two peripheral angles subtend on equal arcs, so more than 2, then it must be equal to each other in their sizes. So if chord AB equals to chord CD, it means that those two center angles subtend on equal arcs, then they are equal to each other in their sizes. That is to say, alpha equals to beta. So we can actually implement rule 30 in our drawing. So first of all, I'll copy this circle in a new page, and I'll copy also center triangle AOB with chord AB that is equals to 8 units in its length, and then I'll do a construction. So in the first step, I copied this circle in this new page. In the next step, I'll copy this center triangle AOB that is equals to what equals in size, and its chord AB that is equals to 8 units in its length. So actually, this is center triangle AOB. Then the coordinate from the original drawing. Center triangle AOB equals to y degrees in its size, and its subset on chord AB. Again, center triangle AOB subset on chord AB that is equals to 8 units in its length. In the next step, I will do a construction. That is to say, from point B, I will draw a chord that its length is equal to 6 units. Again, from point B, I will draw a chord that its length is 6 units. So this is chord BC. This is chord BC that is equals to 6 units in its length according to my construction. In the next step, we will join points O and C together by a straight line. By doing this construction, we created center triangle BOC. Center triangle BOC subtend on chord BC. Again, center triangle BOC subtend on chord BC that is equals to 6 units in its length according to my construction. Now we can implement rule 30 in our drawing. Why? Because in our drawing we have center triangle BOC that is equals to 6 units in its length. In our original drawing we have center triangle POQ. This is center triangle POQ that also subtend on chord BQ that is equals to 6 units in its length, exactly like this center triangle BOC that subset on chord is equals to 6 units in its length. And because of the fact that those two center triangles subtend unequal chords. They must be equal to each other in their sizes. Why those two center triangles subtend unequal chords? Because this center triangle QOP subtend on chord QP that is equal to 6 units in itself. And this is center triangle BOC that subtend on chord BC that is also equal to 6 units in itself. So those two center triangles subtend on equal chords, is equal to 6 units, and therefore they must be equal to each other in their sizes. But the size of this center triangle BOP and the size of this center triangle QOP is x. And therefore the size of this center triangle BOQ that also subtend on chord that is equal to 6 units in itself must be equal to x units according to rule 30. Okay, according to rule 30, center triangles that subtend on equal chords are equal to each other. So those two center triangles subtend on equal chords is equal to 6 units in itself, therefore they must be equal to each other in their sizes. But the size of this center triangle QP is x, therefore the size of this center triangle BOC must be also equal to x degrees in its size, according to rule 30, of course. So by doing this construction, we get that the big angle AOC that equals to x plus y degrees in its size. Again, the big angle AOC equals to x plus y degrees in its size. But we already found out that x plus y equals to 180 degrees. Okay, again, we have already found out that x plus y equals to 180 degrees. So the big angle AOC equals to x plus y that is equals to 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. And because of the fact that angle AOC equals to 180 degrees in its size, AC is a straight line. Writing down. AC is a straight line. But AC is a straight line that touches the circle 2 points, A and C. Therefore, AC is a chord that passes for point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Again, any chord that passes through the center of the circle, must be the diameter of the circle. So we can write down here that AC is the diameter of the circle because it passes from point O, that is the center of the circle. So AC is the diameter of the circle. Here we can implement rule 7. I'll please click on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it must be equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of the circle. Therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So according to rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. We can implement rule 7 in our drawing. In our drawing, we have plane triangle ABC. Plane triangle ABC is sometimes called AC, that is the diameter of the circle, and therefore plane triangle ABC must be equal to 90 degrees in size according to rule 7. In the next step, I copy the right big triangle ABC in the equation. We implement on this right big triangle ABC the Pythagoras theorem. The hypotenuse AC is also the diameter of the circle. So if the radius of this circle is r, then the diameter must be equal to 2r. Side AB equals to 8 units in its length according to what is given as the question. And side BC equals to 6 units in its length according to our construction. Here by PT is the evaluation for Pythagoras theorem. So actually, this is the right triangle ABC, according to the original drawing. This right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So write it down. AC squared, that is the square of the hypotenuse, is equal to AB square plus BC square. AC, the hypotenuse AC is also the diameter of the circle, that is 2r. Therefore AC squared is 2r squared, that is 4r squared, and it is equal to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared, 6 squared, that is 36. 64 plus 36 is 100. So if you found out that 4r squared equals to 100, here we will divide this equation by 4, and we get that r squared equals to 100 over 4 is 25. So r squared equals to 25. Here we take a look out of this equation, and we get that the radius r of the circle is equal to the square root of 25, that is 5. So if you found out that the radius r of the circle is equal to 5 units in its length. Our task is to find out the area of the circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. So it is pi times r squared. R is 5, therefore r squared is 5 squared, it is 25. So in total we actually found out that the area of this circle, that is the area that we are looking for in this question, it is equal to either 25 pi square units in its size, or in terms of numbers, it is equal to 78.54 square units in its size. Repeat again, we should find out that the area that we are looking for in this question, that is the area of this circle, it is equal to either 25 pi square units in its size, or in terms of numbers, the area of this circle equals to 78.54 square units in its size. We finished with the first method. We finished actually with the second method. We finished with the first method of the second question. In the next step, I present to you how to find out the area of this circle according to the second method. In the second method, we will use some of the things that we have already found out in the first method. In the first method, we have already found out that those two angles are both equal to alpha. Those two angles are both right angles. So, if we focus on right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. This is the sum of the angles in a triangle. Likewise, in the right triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. Actually, it is very easy to see that those two right triangles are similar to each other according to angle similarity rule. I will explain anyway why those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if we prove that all the three angles of this right triangle ABM corresponding equal to the three angles of this right triangle PMQ, therefore those two right triangles are similar to each other according to angle similarity rule. So it is known if we found out that the right triangle ABM is similar, this is the sign of similar, to the right small triangle PMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle AMB over side PQ of the right triangle PMQ is equal to side AM of the right triangle AMB over side PM of the right triangle PMQ, and it is also equal to side BM of the right triangle ABM over side MQ of the right triangle PMQ. Repeat again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABM or side PQ of the right triangle PMQ is equal to side AM of the right triangle ABM or side PM of the right triangle PMQ, and it is also equal to side BM of the right triangle ABM or side MQ of the right triangle PMQ. AB equals to 8 over PQ. It is given us the question that PQ equals to 6, here PQ equals to 6. Just forgot to write it here. So PQ equals to 6. And it is equal to AM over PM. So total we found out that 8 over 6 equals to AM over PM. Here we will divide both the numerator and the denominator of this number by 2. 8 over 2 is 4 and 6 over 2 is 3. And it is equal to AM over PM. Here we multiply both the numerator and the denominator of this number by 8. A over A is 1. And it is allowable to multiply anything by y. By multiplying it by 1, you will not change the value of the expression. So the operation is allowable. So we get here that 4a over 3a equals to AM over PM. What is the meaning of this equation that 4a over 3a equals to AM over PM? This equation means that if AM equals to 4a, then PM must be equal to 3a. So, if we found out that if AM equals to 4a, then PM must be equal to 3a. Those two sides of the equation are equal to each other. AB over PQ is 4/4. So 4/4 equals to BM over QM. BM over MQ. Here we multiply both the denominator and the denominator of this number by B. and we get that 4b over 3b equals to bm over mq. What is the meaning of this equation? The meaning of this equation is that if bm equals to 4b, then qm must be equal to 3b. So we should all know that if bm equals to 4b, if bm equals to 4b, then mq must be equal to 3b. This is called PB. And again, this is called PB. PB as a code, it is absolutely a straight line. So if we focus on the right side of the straight line PB at point M here, the sum of the areas must be equal to 180 degrees according to all three. All three says that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angle we have at the right side of PB at point M? We have this angle, this is the right angle, plus this missing angle, in total the sum of those angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points B and Q together by a straight line. By joining points B and Q, we get the right angle MBQ. Repeat again. By joining points B and Q together by a straight line, we get the right angle BMQ. So we copy the right angle BMQ in the new page and we implement only the Pythagoras theorem. The hypotenuse BQ is the missing side. Side BM equals to 4B and side MQ equals to 3B. Here by PT is the evolution for Pythagoras theorem. So actually, this is the right triangle BMQ, the decorator on the original drawing. In this right triangle BMQ, BQ squared, that is the square of the hypotenuse, must be equal to MB squared plus MQ squared. So write it down. BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. BQ is the missing side, so it is. So it's B, so it is BQ squared equals to MB squared. MB is 4B, therefore MB squared is 4B squared, that is 16B squared. Plus MQ squared. MQ is 3B. MQ is 3B, therefore MQ squared is 3B squared, that is 9B squared. 16B squared plus 9B squared is 25B squared. So now we should know that BQ squared equals to 25B squared. Again, if I don't feel that BQ squared equals to 25B squared. Here we take out of this equation and finally we get that the missing side BQ, the hypotenuse BQ, is equal to the square root of 25 is 5 and the square root of B squared is B. Again, BQ equals to 5 B units in its length. So here, this is the missing side BQ, that equals to 5 B units in its length. In the next step, we will calculate the area of this triangle ABQ by using two different methods. And then we create an equation that states that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. So according to the first method, the area of this triangle ABQ equals to the base of the triangle times the height to the base over 2. Repeat again, the area of triangle ABC equals the area of triangle ABQ equals to the base of the triangle times the height to the base over 2. We choose the base as AQ, that is AQ times the height to the base. The height to the base is is BM. Why is BM? Because it creates 9 degrees with the base AQ. So it is times BM divided by 2. So if you found out that the area of triangle ABQ according to the first method is equal to the base AQ times the height to the base, that is BM over 2. And it must be equal to the area of triangle ABQ according to the second method. So we calculate the area of triangle ABQ in a different way. And we calculate the area of triangle ABQ according to a new formula. Actually, this is the right triangle ABC that could be any triangle. The length of side AB is A units, AC equals to B units in its length, and side BC equals to C units in its length. This is angle theta, So in this triangle ABC, the following equation is true that the area of triangle ABC equals to A times B times sinus theta over 2. Again, the area of triangle ABC is equals to A times B times sinus theta over 2. So according to the second method, the area of any triangle equals to the multiplication of two sides by each other times sinus the angle between the two sides. Again, the area of any triangle according to the second method is equals to the multiplication of two sides by each other times sinus the angle between the two sides, A and B. So I can implement the new rule in order to find out the area of this triangle ABQ. According to the new method, the area of triangle ABQ will be equal to AB times BQ, that is the multiplication of two sides of triangle ABQ by each other, times sinus the angle between the two sides. Times sinus the angle between the two sides. So it is sinus angle ABQ. This is angle ABQ. So it is sinus angle ABQ over 2. And again, I should found that the area of triangle ABQ according to the first method is equals to AB times BQ, that is the multiplication of two sides by each other, times sinus the angle between the two sides AB and BQ, that is the angle ABQ divided by 2. So this equation says that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. Here we have 2 on both sides of this equation, so 2 will get cancelled. So in the next step we have to find out the value of sinus angle ABQ. So what is the value of sinus angle ABQ? In order to find out the value of sinus angle ABQ, we will implement the law of sines in our triangle ABQ. The law of sines is true in any triangle. So actually, this is triangle ABC that could be any triangle. Side AB of that triangle ABC equals to C units in its length. Side AC equals to B units in its length. And side BC equals to A units in its length. This is angle alpha, this is angle beta, and this is angle gamma. In this triangle ABC that would be any triangle, the following equation is true. That A over sinus alpha equals to B over sinus beta equals to C over sinus gamma. And it is equal to 2R. 2R is the diameter of the circle that blocks this triangle ABC. Again, 2R is the diameter of the circle that blocks this triangle ABC. Okay, so we can implement the new rule in our drawing. So if you focus on triangle ABQ, according to the law of sines, the following equation will be true. That AQ over sinus angle ABQ equals to 2R. Again, AQ over sinus angle ABQ equals to 2R. And 2R is the diameter of the circle that blocks this triangle ABQ. So according to the law of sines, the following equation will be true. That AQ over sinus angle ABQ again AQ over sinus angle ABQ equals to 2R, and 2R is the diameter of this circle that blocks this triangle ABQ. And again, according to the law of sines, the following equation is true that AQ over sinus angle ABQ equals to 2R. Here we multiply this equation by sinus angle ABQ, and then we divide it by 2R simultaneously, and we get that sinus angle ABQ equals to AQ over 2R. So if you found out that sinus angle ABQ equals to AQ over 2R, so we can substitute sinus angle ABQ in this equation by AQ over 2R. We'll do it now, and we'll get that according to this equation. AQ times BM AQ times BM equals to AB times BQ and sinus angle ABQ is AQ over 2R. So substitute sinus angle ABQ by AQ over 2R. So in total, we found out that according to the law of sines, AQ times BM equals to AB times BQ times AQ over 2R. Here we have AQ on both sides of this equation, so AQ will get cancelled. After I cancel AQ on this side of the equation, we have to only with BM. So BM equals to AB times BQ. AB times BQ. AB times BQ over 2R, of course. Again, in this side of the equation, we have AB times BQ over 2R. So in total, we should found out that BM equals to AB times BQ over 2R. Here we multiply this equation by R, and then we divide it by BM simultaneously. And we get that R equals to AB times BQ over 2R. R equals to AB times BQ over 2 times BM, of course. because we multiplied this equation by R and we divided it by BM simultaneously. So in total, R equals to AB times BQ over 2 times BM. So R equals to AB is 8 times BQ. BQ is 5B over 2 times BM. BM is 4B. So if you find out that R equals to 8 times 5 times B over 2 times 4 times B. We have B in the numerator and B in the denominator, so B will get cancelled. And we have 8 in the numerator and 2 times 4 is 8 in the denominator, so 8 will get cancelled. We have 8 in the numerator and 2 times 4 is 8 in the denominator, so they will be cancelled. So we found out in total that R equals to 5 units in its length. So the radius of this circle equals to 5 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared, but the radius of our circle squared is r squared, so total the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total the area of our circle must be equal to either 25 pi square units in size, or in terms of numbers it is equal to 78.54 square units in size. So, as we found out that in both methods, the area of this circle equals to either 25 pi square units in size, or in terms of numbers, the area of this circle equals to 78.54 square units in size. So, we finish with the second method of the second question. In the next step, I will summarize the lecture. I will start with the first question, of course. In the first question, our test is to find out the area of this big rectangle EFQH. So in the drawing we have rectangle EFQH. Inside this rectangle we have 3 circles. The radius of this small circle is 5, the radius of this medium circle is 6, and the radius of this big circle is 8. Again, our test to find out the area of this big rectangle EFQH. So, first of all, we know that all the angles inside the rectangle are right angles. So, those 4 angles are all right angles. In the next step, I presented to you rule 1, and we implemented rule 1 a lot of times in our drawing. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So, in the drawing, we have a circle OM. This is equals to R, it is the radius of the circle, and we have tangent AB. This is tangent to the circle, it's point M. So according to this rule 1, the radius OM is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, we will implement, I'll explain you how we can implement rule 1 only on one case, and then we do it automatically without any explanations for the other cases. We take for example the medium circle. The radius of this medium circle is 6, and the radius is QB is equals to 6. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this medium circle. And whenever your radius is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BO. If HQ is perpendicular to BO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Then, we implement rule 1. Here, this angle equals to 90 degrees, this angle also equals to 90 degrees according to rule 1. All the angles that are right angles are right angles according to rule 1. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So actually we extended the radius CS. We joined points S and N together by some 9. SL is the radius of this big circle. This equals to 8. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the lower quadrigonal STQL we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees in its size. Likewise in the upper quadrigonal CFST we have 1, 2, 3 right angles, and therefore this fourth angle must be equal to 90 degrees in its size. So if you found out that angle CST, tangent is equal to 90 degrees plus 90 degrees is 180 degrees, so, and you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So CS, CH, this is CL, CL is a straight line because angle CSL equals to 90 degrees and 280 degrees inside, and any angle that is equal to 90 180 degrees inside, it is defined as a straight line. So CL is a straight line, and therefore shape ECLH has 4 sides, 1, 2, 3, 4, and therefore it is a rectangle. In the rectangle, shape ECLH is 1, 2, 3, 4 sides, and therefore it is a quadrilateral. But in quadrilateral ECLH we have 4 right angles, 1, 2, 3, 4. And any quadrilateral that has 4 right angles must be this rectangle plus a square. So in that quadrilateral ECLH is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ECLH, side CL must be equal to the opposite side EH. But CL in total is 8%, that is 16, and therefore the opposite side EH must also equal to 16 instead. In the next step, we extended the radius BQ by side line until it touches side EF from the big rectangle. We define the touching point of the extended radius BQ with side EF. This point is point S. By doing this construction, we can delete quadrilateral ESBH. Inside quadrilateral ESBH, we have 1, 2, 3 degrees, and therefore this fourth missing again must be equal to 90 degrees in its size. Likewise, inside quadrilateral ACLC, we have SBLC. We have 1, 2, 3 degrees, and therefore this fourth missing again must be equal to 90 degrees in its size. In the next step, we did another construction. That is to start from point P, we go perpendicular on SB. So this angle goes to 90 degrees, and this angle also goes to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SB. This point is point X. So actually, by doing this construction, created the small quadrilateral ESXZ. Inside the small quadrilateral ESXZ, we have 1, 2 degrees, and therefore inside quadrilateral SAPX, we have 1, 2 degrees, and therefore this fourth missing area must be equal to 90 degrees in its size. So inside quadrilateral here, the fourth missing area must be equal to 90 degrees in its size. So quadrilateral ASXP is rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle ASXP, side AB must be equal to the opposite side SX. But AP is 5, therefore the opposite side SX must be also equal to 5 units in its length. What is the length of XQ? XQ, actually SB equals to EH equals to 16 because SEHB is a rectangle. Therefore, SB equals to 16. So in total, SQ must be equal to 16 minus X minus 6. Repeat again. Let me see that XQ must be equal to SB, that is 16, minus SX, that is 5. 16 minus 5 is 11. Minus QB, that is 6. 11 minus 6 is 5. So let me say 9 seconds x cube must be equal to 5 units in its length. In the next step, we join points P and Q together by a straight line. We have an external line between the small circle and the medium circle. That is to say, they touch each other. External line is point Y. Here we can implement rule 10. According to rule 10, the straight line that connects the centers together, that is the straight line PQ, must pass for point Y, that is their touching point. Or PYQ is a straight line, according to rule 10. If PYQ is one straight line, it means that PQ equals to PY, that is 5, plus YQ, that is 6. So in total, PQ equals to 5 plus 6 is 11. So in the next step, I complete the right green triangle PXQ in a new page, and we implemented the Pythagoras theorem on this right green triangle PXQ. Okay, this is the right green triangle PXQ. This is the go between the original drawing. And this right triangle PXQ, PQ square equals to PX square plus XQ square. PQ is 11, therefore PQ square is 11 square, that is 121, and it is equals to PX square. PX is the missing side, so it is, plus XQ square. XQ is 5, therefore XQ square is 5 square, that is 25. So in total, we should find out that 121 equals to PX square plus 25. Here we subtract 25 for this equation, and we find out that Px squared equals to 121 plus 25 is 96. So Pq squared equals Px squared equals to 96. Here we took out we substituted 96 by 16 times 6. So 16 times 6 equals to 96. So 16 times 6 equals to Px squared according to this equation. Here we took out of this equation and found out that Px equals to the square root of 16 is 4, so inside the root we left only with 6. So in total Px equals to 4 times square root of 6 units in its length. This is the side Px is equals to 4 times square root of 6 units in its length. APXS is a rectangle, and you know that the opposite sides of a rectangle are equal to each other. So in rectangle ASXP, side PX must be equal to the opposite side AS. But PX is 4 times square root of 6, therefore the opposite side AS must be also equal to 4 times square root of 6 units in its length. So in the next step, we join points Q, that is the center of this medium circle, and point S, that is the center of the big circle, by a straight line. We join points Q and S together by a straight line. And according to rule 10, because we have an external line between the medium circle and the big circle, the straight line that connects the centers together, that is the straight line QS, must pass through point J, that is their touching point. Or QJS is one straight line. If QJS is one straight line, then it means that QS in total equals to QJ plus JS. So QS equals to QJ is 6 plus JS is 8. So in total QS equals to 6 plus 8, that is 14. So QS equals to 14. In the next step, we did the construction. That is to say, from point Q, we do perpendicular on SL. Again, from point Q, we do perpendicular on SL. So this again equals to 90 degrees, and this again also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and CL. This point is point Z. By doing this construction, we get the right triangle QSZ. So here we implement the Pythagoras theorem on this line diagram QSZ. But before that, we know that Q, Z, and B is a rectangle because it has one, two, three rectangles, and therefore this 4 pieces again must be also equal to 90 degrees. So for the Q, S, and B, we have 4 rectangles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle Q, Z, and B, side QB must be equal to the opposite side Z, to the opposite side ZL. But QB is 6, therefore the opposite side ZL must be also equal to 6 units in its length. So, what is the length of the missing element, short element SZ? SZ equals to SL, that is 8, plus ZL, that is 6. 8 plus 6 is 2, so SZ equals to 2. In the next step, we found out that, again, that the short element SZ equals to SL, that is 8, plus ZL, that is 6. 8 plus 6 is 2. In the next step, we copied the line green target QSZ in a new page, and implemented the Pythagoras theorem on this green line target QSZ. The hypotenuse QS is 14, SZ is 2, and QZ is the missing side. So okay, this is the line target QSZ that according to the original domain. According to the Pythagoras theorem, in this line target QSZ, QS square, that is the square of the hypotenuse, equals to SZ square plus QZ square. QS is 14, therefore QS square is 14 square, that is 196, and it equals to SZ square. SZ is 2, therefore SZ square is 2 square, that is 4, plus QZ square. QZ is the missing side, so we leave it as it is. So today we found out that 196 equals to 4 plus QZ square. Here we subtract the 4 from this equation, and finally found out that 196 minus 4 is 192 equals to QZ square. We substitute 192 by 64 times 3, so 64 times 3 equals to QZ square. Here we took a root out of this equation, and finally found out that the missing sign QZ equals to the square root of 64, that is 8. So inside the root we left only 3. So total QZ equals to 8 times square root of 3 units in its length. This is the missing sign QZ, that equals to 8 times square root of 3 units in its length. For the other SCZQ is rectangle because it has 1, 2, 3, 4 right angles. Therefore it is a rectangle, but we know that the opposite sides of a rectangle are equal to each other. So a rectangle CSQZ, side CS must be equal to the opposite side QZ. But QZ is 8 times square root of 3, therefore the opposite side must be also equal to 8 times square root of 3 units in its length. Our test is to find out the area of this rectangle. Actually here we have 4 rectangles, and therefore it is a rectangle in small quadrilateral EAPD is a rectangle. The opposite sides of a rectangle are equal to each other, so DP, that is 5, must be equal to the opposite side EA. So DP is 5, therefore EA is also 5. Likewise, the small quadrilateral CF TS is a rectangle, the opposite sides of a rectangle are equal to each other. So an rectangle CFST, side ST must be equal to the opposite side CF. But STZ, therefore the opposite side CF must be also equal to 8 units in its length. Our test is to find out the area of this circle. The area of this rectangle EFQ edge. We already found out that the width EH is 16, and we already found out that the length EF is 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. And the width times the length is the area of this rectangle EFQH, that is the area that we're looking for in this question. So the area of rectangle EFQH equals to the width times the length. The width is the edge and the length is the EF. Again, the width is the edge and the length is the EF. EH is 16 and EF is AEA plus AH plus SC plus CF. Again, the width is 16 and the length is EA, that is 5, plus SA, that is 4 times square root of 6, plus SC, that is 8 times square root of 3, plus CF, that is 8. In total, the value of this expression is 586.47 square units in size. So if you found out that the area of this big rectangle equals to 586.47 square units in size. Okay. We finish with the first question. In the next step, I presented to you the second question, and we solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. In the drawing, we have a circle. This is called AB, that is equals to 8 units in its length. This is called PQ, that is equals to 6 units in its length. This is angle PMQ, that is right angle. Again, our task is to find out the area of this circle. So first of all, I presented to you Rule 29, and we implemented Rule 29 in our drawing. According to Rule 29, peripheral angles that subtend on equal arcs, and peripheral angles that subtend on the same arc are equal to each other in their sizes. So in the drawing, we have a circle. This is peripheral angle BDC that subtend on arc BC. Likewise, we have another peripheral angle. This is peripheral angle BEC that is also subtend on the same arc BC. And because of the fact that those two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. This is to say, alpha equals to beta. So according to this Rule 29, if peripheral angles subtend on the same arc, they must be equal to each other in their sizes. So we can implement Rule 29 in our drawing. We have peripheral angle BAQ that subtend on arc PQ, and it is equal to alpha divided in size. And peripheral angle BQ subtend on arc BQ. We don't know the size of this peripheral angle. Likewise, we have another peripheral angle BPQ that subtend on the same arc PQ. And because of the fact that those two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. So if the size of this peripheral angle BQ is alpha, then the size of this peripheral angle BPQ must be also equal to alpha, according to Rule 29. In the next step, we focus on this arc AP. We have peripheral angle PQA that's obtained on RKP. Likewise, we have another parameter, that is parameter BPA that's obtained on the same RKP. And because of the fact that those two parameters are obtained on the same RKP, they must be equal to each other in their sizes. So if the size of this parameter PQA is better than the size of this parameter PBA must be also equal to beta according to Rule 29 because the subset of the same arc KP. In the next step, I presented to we define first of all this set of this circle, this point as point O, and I presented to Rule 13 and implemented Rule 13 in our drawing. According to Rule 13, a central angle is twice as large as the peripheral angle subtended on the same chord. On the same chord or the same arcs, doesn't matter. So in the drawing we have a circle. This is peripheral angle ACB that's obtained on RKB. Likewise we have center angle UB that's obtained on the same arc RKB. And because of the fact that peripheral angle ACB equals to theta degrees in its size, then center angle AOB must be equal to 2 theta because it's obtained on the same arc RKB. It must be twice as big as the peripheral angle that's obtained on the same arc RKB. But the size of this peripheral angle is theta, therefore the size of the center angle that's obtained on the same arc RKB must be equal to 2 theta. So according to this Rule 13, the size of the center angle that's obtained on the same arc as the peripheral angle, it must be twice as big as the size of the peripheral angle that's obtained on the same arc. We can implement Rule 13 in our drawing. In our drawing, if we focus on this arc RKP, we get center angle UP that's obtained on RKP. But we also have peripheral angle PQA that's also obtained on the same arc RKP. And the size of peripheral angle PQA is better, therefore the size of the center angle EOP the subset of the same arc RKP must be equal to 2 beta. This is twice as big as this peripheral angle, the subset on the same arc RKB. Likewise, we can add the peripheral angle BOQ, that's subset on arc BQ. But we also have peripheral angle BAQ, and subset on the same arc BQ, and it is equal to alpha. Therefore, the size of the center angle BOQ that's subset on the same chord BQ must be equal to 2 alpha. It is twice as big as this peripheral angle that's subset on the same arc BQ, according to Rule 13. In the next step, we define this angle as y and this angle as x. We have the rule that the sum of the angles around any point is equal to 360 degrees. The sum of the angles around point O must be equal to 360 degrees. That is to say 2 alpha plus 2 beta plus x plus y. In total, the sum of those 4 angles must be equal to 360 degrees. And again, the sum of the angles around point O must be equal to 360 degrees. That is to say 2 alpha plus 2 beta plus x plus y equals to 360 degrees. But we already found out that 2 alpha plus 2 beta equals to 180 degrees. Therefore, we can substitute 2 alpha plus 2 beta in this equation by 180 degrees. So 180 degrees plus x plus y equals to 360 degrees. If we subtract 180 degrees from this equation, if I found out that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. In total, if we found out that x plus y equals to 180 degrees. In the next step, I presented to you Rule 13, implemented Rule 13 in our drawing. According to Rule 30, set angles that obtained on equal chords are equal to each other. So in the lower we have a circle. This is center angle COD that's obtained on code CD. We have another center angle AUB that's obtained on code AB. So if code AB equals to code CD, it means that those two center angles subtend on equal chords, then they must be equal to each other in their sizes. That is why alpha equals to beta. So if two or more center angles subtend on equal chords, they must be equal to each other in their sizes, according to this rule, rule 30. We can implement rule 30 in our drawing. So first of all, I copy this circle here in a new page. Those two circles are identical circles. The center of the circle is 8.0, and I also copied center angle AOB that is equals to y degrees in size, and it's subset of code AB. In the next step, I did a construction, that is to say from point B, I draw a chord BC that is equal to 6 units in itself according to our construction. Again, chord BC equals to 6 units in itself according to my construction. The next step, we join points O and C together by straight line. By doing this construction, we can then center angle COB that's subset of chord BC that is equals to 6 units in its length. Likewise, in the original drawing, we have center angle POQ that's subset of chord PQ that is also equals to 6 units in its length. And because of the fact that those two center angles are both subset on equal chords, chord QP equals to 6 and chord BC also equals to 6. So because of the fact that those center angles subset on equal chords, they must be equal to each other in their sizes. But the size of this center angle QP is x, therefore the size of this center angle BOC must be also equal to x degrees according to rule 30. According to 30, center angles are subset on equal chords like here, they must be equal to each other in their sizes. So if the size of, because of the fact that the size of this center angle BOP is x, the size of this center angle BOC must be also equal to x because they subset on equal chords. Chord BC, chord BP equals to 6, and chord BC also equals to 6. So this operation is the implementation of rule 30 in our drawing. So in total, we found out that the big angle AOC is equal to x plus y degrees in its size. But we only found out that x plus y equals to 360 degrees. So x plus y equals to 180 degrees. So it means that the big angle AOC equals to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. Therefore, AC is a chord. AC is a chord that passes through the center of the circle, that is to say point O. And you know that any chord that passes through the center of the circle, it must be in the diameter of the circle. Therefore, AC that passes through point O, that is the center of the circle, must be the diameter of the circle. So AC is the diameter of the circle. Now we can implement rule 7. Now we're going according to rule 7. If a peripheral angle subtends on the diameter of the circle, then it must be equal to 90 degrees in its size. In the moment we have a circle, this is peripheral angle ACB that subtends on chord AB, that is the diameter of the circle. Therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size, because it subtends on the diameter of the circle. We can implement rule 7 in our drawing. Because in our drawing, we have peripheral angle ABC that is also subtend on the diameter of the circle, that is called AC. Therefore, peripheral angle ABC must be equal to 90 degrees in its size according to rule 7. In the next step, we'll comment the right triangle ABC in the new page, and we implemented the Pythagoras theorem in this right triangle ABC. Okay, this is the right triangle ABC, that is correct from the norm in this triangle ABC. According to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. AC is the numerator of the second, that is 2r, therefore AC squared is 2r squared, that is 4r squared, and it is equal to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. So in total, 4r squared equals to 64 plus 36, that is 100. So 4r squared equals to 100. Here we divided this equation by 4, and we found out that r squared equals to 100 over 4 is 25. R squared equals to 25. Here we took out of this equation, and we found out that the radius r of the circle equals to the square root of 25, that is 5. So the radius r of this circle is equal to 5 units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. And therefore the area of one circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So in total, the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total, if you found out the area of this circle, that is the area that we're looking for in this question, it is equal to either 25 pi square units in size, in terms of numbers. The area of this circle equals to 78.54 square units in size. We finish with the first method. In the next step, I present to you how to find out the area of this circle according to the second method. In the second method, we used some of the fields that we already found out in the first method. In the first method, we have already found that those two angles are both equal to alpha, those two angles are both 90 angles, so we used it in the second method. So in the domain we have the right triangle A and B. In the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this part missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in this triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum, then the sum of the angles in a triangle is equal to 180 degrees. Those two triangles are similar to each other according to angle similar to. Because those two angles are both equal to alpha, those two angles are both equal to 90 degrees, and those two angles are both equal to 90 degrees minus alpha. And from the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle A and B over side PQ of the right triangle PMQ equals to side AM of the right triangle A and B over side PM of the right triangle PMQ. It is also equals to side VM of the right triangle A and B over side MQ of the right triangle PMQ. Repeat again. We will derive that AB over PQ equals to AM over PM equals to BM over MQ. AB is 8, PQ is 6. 8 over 6 is 4 thirds, so 4 thirds equals to AM over PM. Here we multiply both the numerator and the denominator of this number by A, and we found out that 4A over 3 equals to AM over PM. What is the meaning of this equation? The meaning of this equation is that if AM equals to 4A, then PM must be equal to 3A. So if AM equals to 4A, then PM must be equal to 3A. Likewise, those two sides are also equal to each other. AB over PQ is 4 thirds, so 4 thirds equals to BM over MQ. 4 thirds equals to BM over MQ. We multiply both the numerator and the denominator of this number by B, and found out that 4B over 3B equals to BM over MQ. What is the meaning of this equation? The meaning of this equation is that if BM equals to 4B, then MQ equals to 3B. And again, according to this equation, if BM equals to 4B, then MQ must be equal to 3B. PB is a chord in this circle, PB as a code, it is absolutely a straight line. So if we focus on the right side of the straight line PB at point M, if the sum of the areas must be equal to 180 degrees according to all three. All three said that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have the right side of PB at point M, we have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. So in the next step we join points B and Q together by a straight line. By joining points B and Q, we get the right triangle B and Q. The next step, we'll go with the right triangle B and Q in a new pattern. We implemented the Pythagoras theorem on this right triangle B and Q. So okay, this is the right triangle B and Q that is coming from the original domain. In this right triangle B and Q, according to the Pythagoras theorem, BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. BQ is the missing side, so limiticity, so it is BQ squared equals to MB squared. MB is 4B, therefore MB squared is 4B squared, that is 16B squared, plus MQ squared. MQ is 3B, therefore MQ squared is 4B squared, that is 9B squared. So we found out that BQ squared equals to 16B squared plus 9B squared. 16B squared plus 9B squared is 25B squared. So BQ squared equals to 25B squared. Here to hold all of this equation, we found that the missing side BQ is equals to the square root of 25 is 5 and the square root of B squared is B. So total BQ equals to 5B units in its length. This is the missing side BQ that is equals to 5 units in its length. In the next step, we calculate the area of triangle ABQ by two different methods. And then we created an equation that states that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. According to the first method, the area of this triangle ABQ equals to the base AQ times the height MB over 2. According to the first method, the area of triangle ABQ equals to the base AQ times the height to the base BM over 2. According to the second method, the area of triangle ABQ equals to AB times BQ times sinus angle ABQ over 2. The area of triangle ABQ equals to AB times BQ times sinus angle ABQ over 2. We have 2 on both sides of the equation, so 2 will get cancelled. What is the value of sinus angle ABQ? In order to find out the value of sinus angle ABQ, we implemented the law of sines in our drawing. According to the law of sines, the law of sines is for a triangle. This is triangle ABC, this is for any triangle. The length of side AB is C, side AC equals to B units in its length, and side BC equals to A units in its length. This triangle ABC that could be any triangle, the following equation is true, that A over sinus alpha equals to B over sinus beta equals to C over sinus gamma equals to 2R. 2R is the diameter of the circle that blocks this triangle, triangle ABC. So we can implement the law of sines in our drawing, because in our drawing we have triangle ABQ that is blocked by this circle, right? Triangle ABQ is blocked by this circle. According to the law of sines, the following equation is true. AQ over sinus angle ABQ equals to 2R. And 2R is the diameter of this circle that blocks triangle ABQ. According to the law of sines, the following equation is true, that AQ over sinus angle ABQ equals to 2R. Here we multiply this equation by sinus angle ABQ and then we divide it by 2R simultaneously. And finally found out that sinus angle ABQ equals to AQ over 2R. Now we can substitute sinus angle ABQ by AQ over 2R. We did it, and we found out that AQ times BM equals to AB times BQ times AQ over 2R. We have AQ on both sides of this equation, so on both sides of this equation, so AQ will get cancelled. After cancelled AQ, we found out actually that BM equals to AB times BQ over 2R. Here we multiply this equation by R and then we divide it by BM simultaneously. We found out actually that R equals to AB times BQ over 2 times BM. So R equals to AB is 8, BQ is 5B over 2 times MB. BM is 4B. We have B in the numerator and B in the denominator, so B will be cancelled. We have 8 in the numerator and 2 times 4, that is 8 in the denominator, so those numbers will get cancelled and the left will be 5. So we found out that the radius of this circle R equals to 5 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle is equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared, so the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So the area of our circle must be equal to 25 pi square units in size. So in terms of numbers, this is equal to 78.54 square units in size. So in both methods, we actually found out that the area of this circle, that is the area that we are looking for this question, is equal to either 25 pi square units in size, or in terms of numbers, the area of this circle equals to 78.54 square units in its size. Okay, thank you very much.